Good afternoon, everybody. Welcome to this afternoon's session. After a certain mild perturbation, Seonhee Lim has kindly agreed to step in and talk to us about Euclidean algorithms over quadratic imaginary fields are Gaussian.
Thank you very much. Thank you for the introduction. I'd like to first thank Anish and other organizers for the invitation. It's very nice to be back in India. I thought I have 2 more days to prepare, so I was going to start preparing this evening. Okay, so let's see where we go, how we go. All right, so I'd like to talk about complex continuous fraction expansion, but let me start with real continuous fraction expansion. So let's say that we have a real number x between 0 and 1. And so we're talking about the usual continuous fraction expansion, right? So if you have a point between 0 and 1, so we want to know, so the usual continuous fraction expansion, as we've seen this morning. So we're typically taking an irrational number, so there'll be an infinite sequence here. And so attached to this usual continuous fraction expansion is the Gauss map that is 1 over x minus the integral part of 1 over x. Okay, so if you plug in x here, then you'll have a1 plus etc., and then you take away a1. So if you start with this x, that we write as a sequence of a1, a2, etc., then t of x will be a2, a3, etc. Right? So in terms of this sequence AIs, the digits of the usual continuous fraction expansion, the Gauss map is forgetting a1. So it's a shift map. So shift map is what we like a lot in dynamics. And so we can go on and on. So AI will be ti minus 1 of x, 1 over ti minus 1 of x, the integer part of it. So that's the usual continuous fraction expansion. And so some remarks. So basic facts are that AI corresponds to the number of consecutive EI with the same sign. So I'd like to remind you that the digits here that you see in the usual continuous fraction expansion is related to geodesic flow. So say GT on the hyperbolic plane mod SL to Z. So okay. I still have some time, I guess. So if you look at the usual fundamental domain of SL to Z, here we have this vertical fundamental domain, and then we have a bunch of copies of this fundamental domain. And the correspondence between AI and the geodesic flow is as follows. So we can choose so that the endpoint, the forward endpoint of a geodesic is x is between 0 and 1, and we have this continuous fraction expansion, 1 over a1, over a2, etc. Okay, so the basic idea comes from the fact that here, the Gauss map, we have inversion here, 1 over x, and then translation by some integer, right? And we know that both, so we don't have exactly the inversion, but more or less the inversion. So sending z to negative 1 over z. So this is this, and 1, 1, maybe 1, negative 1, 0, 1, sending z to z minus 1. They're both in SL to Z. That's why this Gauss map and the modular surface SL to Z, H2 mod SL to Z, they go well together. So what happens when we do the Gauss map 1 over z minus the integer part of 1 over z? So first we do the inversion, so respect to this circle. And then we're subtracting, so we're applying 1, negative 1, 0, 1 many, many times until we go back to a point between 0 and 1, right? So what we do is we're using this element once, and then we're using this element many times until we come back more or less to the similar picture. So AI corresponds to, so it amounts to saying that AI corresponds to, if you have this geodesic, we're talking about this map, first return map to the compact part. Here, the compact part is more or less this part of the fundamental domain, okay, on the boundary of the fundamental domain. So, and then this number of vertical fundamental domain that we have to pass before we come back to Pn over Qn is the best one. Okay, and then using just pigeonhole principle or Dirichlet theorem, so pigeonhole principle on these intervals, so Q and Qx. So you can show that there exists P and Q such that Q is less than N and Qs minus P. So the distance between 0 and one of those points is less than 1 over N, so it's less than 1 over Q. So we know that it's always true that X minus P over Q is less than 1 over Q squared. But that's inequality that holds all the time. But if we now specify X, it depends on X whether we can improve it or maybe we cannot improve it. So maybe we'll be interested in making improvement by making 1 by epsilon, maybe for some small epsilon. And we say that X is badly approximable if it is far from that. In other words, there is some C, positive C, such that for every P over Q, the error between this badly approximable irrational number and P over Q is bounded below by C of Q squared. And so, and then badly approximable approximability corresponds to AN being bounded. So it is, in turn, if and only if the geodesic corresponding to the forward endpoint being X, this excursion does not go deep in the cusp. So it stays in some compact part. So for example, just by ergodicity, badly approximable numbers has measure 0 by the ergodicity of the geodesic flow because it has to, cover the whole modular surface. Okay. And so it's not part of what I want to say today, but I just wanted to give some kind of broad picture. So let me mention that this can be vastly generalized to vectors and matrices, etc. So if the geodesic flow on the modular surface can be generalized to diagonal flow on SLNR now, mod SLNZ. And SLNR mod SLNZ, you can think of it as the volume 1 lattices in Rn. And asymptotic geometry is that we have a picture very similar to modular surface. So there are many ways to look at it geometrically. You can think of boundaries in a Lie group sense, homogeneous space sense. But here we're looking at only the asymptotic geometry. So by Mahler compactness criterion, if you have a subset of the space of lattices, this set is, should I say, pre-compact. The closure is compact if and only if every point in the lattice, in this set of lattices, every point meaning every lattice, the length of shortest vector is bounded below. So in other words, the maximum of 1 over the length of shortest vector is bounded above. Okay, so this length of 1 over length of shortest vector plays the role of the height. So if you're more than in dimension more than 2, then it's possible to have one vector, one very short vector, but again another very short vector, so that so the area spanned by these two vectors is much smaller than the length of this vector and the length of this vector, right? So if you want to be more precise, then the length of a shortest vector, 1 over the length of shortest vector is not enough. So we have to keep track of not only length of shortest vector, but also area of smallest area spanned by two vectors, etc., etc. All the sub lattices. So parametric geometry of numbers by Schmidt, Zamora, Roy, Das Fishman, Simmons, Rubansky, and others, Poels, etc. Many people. They keep track of length of shortest vector, second second shortest vector, etc. So successive minima of the lattices. Okay. So that's more or less what I wanted to say about Diophantine approximation and homogeneous dynamics. So let's go on. Oops. Oh. Okay, so today I'd like to talk about distribution of length of continuous fraction expansion of rationals. So we were talking about rational numbers. And so let's look at, we're still in the real case. So let's look at the set A over C, where C is bounded above by n, and it's in a reduced form. And if you have such a rational number, we'll say that the length is n, L of x is n, if the continuous fraction expansion is of length n. And what Baladi and Vallée showed is that the distribution of the length of the continuous fraction expansion on sigma n, omega n, is asymptotically Gaussian with the speed of convergence, O, big O of 1 over square root of log of n as n goes to infinity. And using that, they show that if you can even you can measure the length of a continuous fraction expansion, or instead of that, maybe you can fix a number and see how many of AIs have that number, right? So that there are many ways we could. There are many questions we could ask. So according to the question, we could have some more general function C, which is the digit cost function. So for each AI, you could just, C of AI could be just 1, or it could be 1 if it is, AI is certain fixed number that we're interested. Okay? And then we need some condition on the growth. They need some condition on the growth. With that condition, then they show that, Baladi and Vallée show that C of x is asymptotically Gaussian. Okay, so today I'd like to talk about the complex continuous fraction expansion, so generalization of what Baladi and Vallée did for other fields. So we're interested in Q joint square root of negative d. So the ring of integers, instead of z, we will have z or joint square root of negative d if it is not 3 or not 4, and z of 1 plus square root of negative d over 2 if it is modulo 3 modulo 4. But we want this Euclidean algorithm to be reasonable, right? For example, if we start with a rational number, we want this algorithm to finish at some point. So if you do the Euclidean algorithm, if you divide by q, you want the remainder to be smaller than q, right? So that you stop at some point if you have a rational number. And that happens exactly when d equals 1, 2, 3, 7, 11. There are just 5 cases where it is norm Euclidean. So these are the fields that we're interested in. And then, so here we had this classical flow function, the integer part of 1 over x. But now we have to choose which integer we want to take as the integer part. Right? So that amounts to choosing a fundamental domain, so kind of canonical, natural fundamental domain. And that's what we're going to do. So for d equals 1, for example, so d equals 1 is the case when we have z or joint I, right? So we have we're going to take the nearest integer continuous fraction expansion. What it means is that you have C and Z or joint I, so it's A plus BI for A and B integers. And we're choosing the closest one, So to do that, we're going to choose that's the fundamental domain of Z2 action, addition, Z2 action. So it will be just this. I want exact fundamental domain so that we have a unique integer that is yes. So probably we have one of these two. I don't know. Okay, so we're going to choose this rectangle, or in this case, when d equals 1, it will be just a square as the fundamental domain of Z2 action. And this will determine the integer part. Okay, so we're going to shift. So we start with a closed square, and then you translate them. So in the right-hand part or the upper part, and then we're going to subtract those parts. Okay, so that's the fundamental domain. Okay, so if d equals 3, 7, and 11, then we need to be a little more careful. So that's in that case, the canonical fundamental domain will be a hexagon. Okay, for example, when d equals 3, we have a right hexagon here. Anyway, so we have this fixed fundamental domain. Once you have the fixed fundamental domain, then for every z, every complex number, there's a unique integer for us, such that if you subtract, then it will be inside. So this interior means this domain. Okay, so including these boundary, but not these boundaries. Okay, so that yes. So in this case, so we can think of it as the nearest integer continuous fraction expansion. Okay, so there's a choice in the fundamental domain. Yes. I think it is still canonic in some sense, yes. But there are some other ways. For example, when d equals 3, 7, 11, you can also take a rectangle so that everything works out. But we didn't choose those. Okay, so that's how this integer part is determined. And once we determine that, then we can define the Gauss map exactly as the real case. So that's the nearest integer Gauss map. So it was first studied, I believe it was first studied by A. Hurwitz in 1887. So actually there are two brothers, Hurwitz, and they both looked at continuous fraction expansion, different complex continuous fraction expansion, and A. Hurwitz is the one that looked at this nearest integer continuous fraction expansion. And so it was, more recently, it was studied by A. Nakada and Natsui, and they show that it is ergodic. And they also show that the invariant measure, it is absolutely continuous with respect to the area, the usual Lebesgue measure, Haar measure. And it was also studied by Hensley, Bujold, Robert Hurston, about metric Diophantine approximation. Okay, so in this case as well, we're going to look at the digit cost function. So you can just think of it as 1 if you want, or it's 1 if you're interested in a certain number, if alpha j is that number. And then we can look at the same question, whether C of x is asymptotically Gaussian. And so everything I say today is a joint work with Dohyeong Kim and Jungwon Lee. And so we found out that it is still true. In other words, there is these constants depending on the cost function c, so that Cn minus mu n, some constant times n, over d times square root of n, so is a normal distribution. Okay, and yes, I'm going to get there. Yes, thanks. Okay.
Sorry, did you say that the length function that you gave as the first example, is that where c was just 1?
1, yes. Okay, So why were we interested in? So the corollary of the first theorem is that for any u, any real number, and omega n, so it's the same. Instead of now, we have to change a little bit. So before the denominator was bounded above by n, now the height squared should be, the height squared, you can just think of it as b eventually. So it's same as q squared. So q squared is bounded by n. Then the distribution of the total cost function C is asymptotically Gaussian. And you can make it more precise. So yeah, let me skip that. And so what is the corollary of corollary, or motivation of motivation, is that the value of C mod Q for Q in n are equidistributed on this sigma of n. And so in other words, for every A in Z mod QZ, the probability of having the digit cost being A mod Q given inside omega n is 1 over Q. So, all right, so now the motivation of motivation of motivation is that, so we're interested in, we're interested in certain L function, mod P, and so we want to show that some L function is non-vanishing, but instead we cannot show that, so we want to show mod P non-vanishing, and we cannot show that, so we show, so that this is needed. With this, we can show that on omega n. So ideally, we would like to show that if the height is equals n, then you have some L function value is non-zero, but instead, we have some average statement. So, right, so yeah, I'm not an expert in L functions, so let me just say that Bianchi modular symbols have normal distribution and residual equidistribution, and that was the motivation of this work. Okay. All right, so now let's go a little more into the complex Gauss map, the nearest integer complex Gauss map. What's the biggest difference with the usual real continuous fraction expansion or real Gauss map is that the inverse branches of T are not full. So in the real case, the Gauss map looks like this. So it looks like this. So for each, so it should be many more. So for each of branches, 1 over m and 1 over m plus 1, we have the image is everything, right? Whereas in this case, we don't have that. So that's the biggest difference. So if you're given an integer alpha in Z adjoint I, O of alpha, we gather all the elements. So I is the fundamental domain that we had, the rectangle or the square. You look at all the numbers that start with alpha. The continuous fraction expansion starts with alpha. Okay? So this O alpha is not everything. It can be even empty. So it's empty for very small alphas. For most alpha, they're very nice. We can even, you can easily compute the ones for which O alpha is empty. But even when it is not empty, it can be not whole I. Okay? So now we can look at the Gauss map restricted to O alpha. So on this O alpha, we know what to do for the Gauss map because we know that it starts with alpha, right? So it's Z will be sent to 1 over Z minus the integer part, which is alpha, right? So it's 1 over Z minus alpha. So when it is restricted to O alpha, we have bijective maps, okay? For each alpha, for which O alpha is not empty, we have this bijective map. So now we can talk about the inverse, so inverse branch of O alpha. And we know exactly what to do. If you're given Z, then we should send it to 1 over alpha plus Z because, yeah. All right. So where is it defined? It is defined in T of O alpha, the image of T restricted to O alpha, which is not always everything. Okay, so it goes from T O alpha to O alpha. And so for most of alphas, it is everything, this whole square. But for some alphas, it is not everything, it is not empty. Okay, so that's the complications that we have compared to the real continuous fraction expansion. Okay, so we cannot use the method of Baladi and Vallée because of that property. Pardon? I is the square, the fundamental domain for this C2. Yes. Okay, so we started thinking about this problem in 2018, and then for many years we were stuck. And then around 2021, we saw this paper by Nakada, Natsuki, and A, and that's where we found how to overcome the problem. So the structure is the cell structure. So this T of O alpha, it looks like these. So if you do this for the small O alphas, then you can easily see that. So you have this I here, and you have some of TO alpha looks like this, so like this. Some of them can also look like this, etc. And then you can kind of guess that, oh, maybe it is unions of these pieces. And that's exactly what it happens here. So what we want, so the goal is to make it, so why do we want this, why are we interested in this? Because soon you'll see a transfer operator. And in this transfer operator, we have a characteristic function on TO alpha. So we wanted this characteristic function on TO alpha to be C1. Okay? So we wanted to have these piecewise C1 structure. So what's the structure, the cell structure? So one typical example of T, so when alpha is 1 plus I, TO alpha looks like this. And so we can see that actually there's this cell structure. So we have these two cells, so open two cells and open one cells and vertices. So that altogether we call it P is the partition. So open two cells, open one cells, and points. And it behaves very well under the Gauss map. So we say that this cell structure is compatible with T if and only if TO alpha is always a union of those two cells and one cells and zero cells. So this joint union, for example, this one, the TO alpha when alpha is 1 plus I, it is a union of these two cells, this two cell, and these two cells, plus all the boundary cells. Okay. So first of all, so we say that P is compatible with T, the Gauss map, if and only if, first of all, we want this sort of Markov condition that TO alpha is a disjoint union of cells. We have only finite cells. And secondly, every inverse branch H alpha is the inverse branch of O alpha. There is this, for every P, either it goes outside, if you apply H alpha, it goes outside the square, or there is a unique Q. Q is one of these cells, so that it goes entirely into one of those cells. Okay, so using this structure, now we can define, so what is the space of functions that we work on? It's the C1 of P, which are functions that are, when restricted to all these cells, they're continuous, they extend to a continuous differential function on some open neighborhood of each of these cells. So that's the space of functions that we will be playing on. And it is, you can think of it as the direct sum of C1 of P closure. And if you have a function, you can think of it as finitely many tuples of C1 functions on each of the cells that we just defined. And so it's a theorem of, it's not exactly a theorem of Nakada and other people, but it follows, with some work, we can show that for D1, 2, 3, 7, 11, there is some cell structure compatible with the Gauss map. And using the property that Nakada and his collaborators call finite range property. Okay, so now let's see how to show this Gaussian distribution, asymptotic Gaussian distribution. So we need to, we use weighted transfer operator, weights related to the digit cost function. Okay, so for two complex numbers s and w or omega, A will be all those alphas for which O alpha is non-empty. So except finitely many very small alphas, they're all non-empty. And so now we're going to think of digit cost as a function on O alpha. So if z is in O alpha, we know that it starts with alpha, right? The first A1, the first digit is alpha. So we are going to take the digit function of alpha as C of z. And looking at this way, the Jacobian of H alpha, so it's the inverse branch of the Gauss map, seen as R2 function is, so you can think of it as the holomorphic derivative squared. So that's the J alpha. And so that's going to appear here in the weight. So this is the weight of the weight transfer operator, where the weight is half digits. So exponential, so it's more or less, so it's exponential of something. This is like a potential, right? So C is the digit cost. And then we have the Jacobian of the Gauss map at the integer part of C inverse. So that's like the first digit, A1 or alpha, if you want. And then you have power S. So that's the weight that we need for the weighted transfer operator. So now what's the transfer operator here? So typical transfer operator is like summation of f of z over all the inverse branches, right? Inverse image of the given point. Instead, we have this weight that was given here. And and then using the fact that we have these inverse branches, H alpha. So H alpha, so T of Z0 is Z. So we're taking all these inverse branches. H alpha of Z is Z0. Now we can think of it as a sum weight with weights, the same weights. But now we have this characteristic function of TO alpha. As I said, we wanted this to look at, we wanted to see this as a living in the C1 space. That's why we had this characteristic function of TO alpha, and we wanted that to be a C1 function. Okay, so, right. So if you're given, so more, right, so we have a bunch of finite tuples. If you're looking at a function P coordinate of that, not coordinate, P entry of that function, it will be summation of all the Q's. Q's are there are only finitely many ones. So these cells, 2 cells and 1 cells, we have a summation of that, and then summation over all the inverse branches of Gauss map. So now it seems nicer as a function. And so we had this question of moderate growth. So we want this function to be convergent. So we want this function to make sense. So we want this summation here to be convergent. So moderate growth would be the least, the weakest definition would be so that this formula makes sense, so that it is convergent. So as long as it makes sense, then, so yes. Maybe we should skip. Okay. So more precisely, C is called moderate growth if and only if there is some neighborhood of 1, 0. So this was S and this was W. So S is here. So it's when we have just Jacobian, and 0 is when weight is just 1. Okay. so neighborhood of 1, 0, so that for every point in that neighborhood, so we are taking the neighborhood, real neighborhood of 1, 0. So if the real part of your complex parameters are in some neighborhood of 1, 0, then this exponential of the weight times the Jacobian power s is convergent. Okay, so what kind of properties we can get? So first of all, we have some analog of Perron-Frobenius function theorem saying that for s in this, so when for this s and w, for which the real part is in this neighborhood, there is a spectral gap. So in particular, this weighted transfer operator has an eigenvalue, lambda, of maximum modulus, and all the other eigenvalue of modulus, there are no other eigenvalue of the same modulus. And that eigenvalue is algebraically simple. And then we have to go through the Dohyeong type estimate. So we have to show that, so there is some c and sufficiently large t for, yes, I didn't define the norm here, but we need to bound this t norm. It's more or less like a Sobolev norm. It's the derivative, the supremum norm plus 1 over t of the derivative, sup of derivative. Anyway, so this norm should be bounded by t to the c. Right, so I just said that. Oh, right, so what's the, so it changes a little bit because we have to take into account that we have piecewise C1, so we are just taking maximum of the supremum norm and maximum of the supremum norm of the first derivative over all the finite cells. So we have finitely many cells anyway, so it doesn't make much difference. I mean, everything goes through very well. And yeah, with topological mixing of the Gauss map, we get the Perron-Frobenius theorem using Lasota-Yoke inequality. Let me not go into it. Yes. So Lasota-Yoke inequality says that is to show that the inequality is saying that one norm of Ln you can bound by some constant times another norm, zero norm, sum norm, and the one norm. So we need these two norms to play with and to have some inequality. And then using the cell structure, using the dual system, and some sort of two-dimensional van der Kolk lemma, you can also show the Dohyeong type estimate. So this dual system is something that is still mysterious for me. Maybe I can go back to that at some point. Right, so now, so you can think of resolvent as a Dirichlet series. So let's think of this point. So this is the origin. Origin is always, so here this is just a vertex, right? So it's part of the cell structure. It's a zero cell. So it's in P of 0, and you're plugging in 0. So if you plug in 0 and of the Ln of the characteristic function 1, just constant function 1, then we get this summation. And so if you can iterate, right? You can iterate the transfer operator n times. So we are looking at the summation over all the alphas. Now we have all the first m digits of the continuum fraction expansions are fixed. For those, we can have the summation of C of alpha i's, and then Jacobian of H alpha composition from alpha 1 to alpha n. Okay, so that's what we are looking at. And and then we have a contraction ratio which is less than 1. So that's a very crucial part, that for this composition of inverse branches of the Gauss map, we have a contraction ratio which is less than 1. Right, so using that, we can think of it as, we're looking at only the rationals, right? So we can think of it as the limit as n goes to infinity of all the rationals of denominator bounded by something. And then we have the same formula. And so, right. So this is the motivation part that I mentioned a little bit. So the L function that we are interested in, you can express it as the resultant of the weighted transfer operator. And unfortunately, we have this omega n here, whereas we wanted to know the value on sigma n, where the height is fixed. Anyway, so we can get this mod p. Average version of mod p non-zero property of the L function. So it has a unique simple pole as S is near 1. This is bounded by some alpha 0. And we can have the bound on the value. So it is less than max of 1 or t to the t power cube c. And then, so there's a typical last part that we have to do. We have to apply some Tauberian theorem twice, or you can do it once using Perron formula. Yes. Oh, yes. So now it's towards the end of my talk. So I wanted to, so to me, there's still this dual system that I don't understand very well. So what is the dual system? So it is given by Nakada and his collaborators. It was used, in their paper, it was used to extend Gauss map. So Gauss map is like forgetting A1, right? So it's a shift map forgetting A1. So it's one-sided shift map. So sort of natural extension to make it bijective is to make it two-sided shifts. Right? So we want to do something similar to that. So the first part we want to be just a Gauss map. And we want to add something in the later part, which they call P star. It's a dual. And so that we have a natural extension on some subset of union of all those P times P dual of P. But this P star, the dual, is very hard to grasp and hard to draw how it looks. So it is easily defined. It's the closure of T tilde n of Z0. So this is, we have only the first part, so it's just the Gauss, the usual Gauss map on the first coordinate. But yeah, and then we have the dual I star, which is just the union of dual of P. And so it's what we know. The only thing, more or less the only thing we know is that it is in the unit-circle. But we don't know exactly how it looks. So how do you see how it looks? We can use the fact that actually, if you have alpha 1 to alpha n, you revert the order. So you start with alpha n, and you end by alpha 1. And that corresponds to P. So it amounts to, so yes, I should stop in a couple of minutes. So if you have alpha 101 alpha, you multiply them, you get the principal convergence, right? So instead of alpha 1 alpha n, you reverse the order, and then you'll get the number, the rational that corresponds to a point in the dual point, dual P of P star. So using that, we can vaguely find what we have. So instead of Pn minus 1 over Qn minus 1, Pn over Qn, if you revert these matrices, you'll have Pn minus 1 over Pn and Qn minus 1 over Qn. That's how you guess. And then so this is given by just plotting this Qn minus 1 over Qn. So it's more or less the picture. But limit of this picture will give us I star. Okay, so this is when d equals 1, so z a joint of I. Yeah, please right. Disregard this. Okay, so these are the ones that we have hexagonal fundamental domain, Anyway, so all we know is that it is in the unicircle, but we don't know exactly how it is. For example, we see that there are these some are punctures, maybe. I don't know. I don't think there should be, but yeah. So it's not known. It's not known that it is simply connected. Yeah. So yes. So that's all I wanted to say. So let me finish up with the picture of this cell structure. So when d equals 1 is rather easy. You just go one step, and then you can get all those cells, but sometimes it can be very hard. So you have to go several steps, and you realize that it stabilizes. But I don't think there is a conceptual proof that it should stabilize. Okay. Yeah. This, yeah. So this is the picture for d equals 11, given to us by Nakada and his collaborators. Let me stop here.